for the I'm very glad to come here to talk to many people, very inspiring discussions, and I'm very glad to present here. The first part of my title is 4D seismic interferometry. This is the technique that I use. 4D here means one dimension in time plus 3 dimensions in space. And the second part is new perspectives of groundwater monitoring and beyond. That means my talk today will be focusing on one monitoring application about groundwater fluctuations in California. But this seismological approach I present here can also be applied to monitor many other time-varying processes in shallow subsurface. So the time scale of these processes are typically, say, a couple of days to a few decades. And the spatial scale I'm looking at is typically within meters to a few kilometers below the surface. Sorry, I'll stop share for students. Share. Yes, thank you. So I'll start with this heat waves around the globe. So in this past summer, we saw wave after wave of heat crested and broke around the world. This globe illustrates the air temperature in the Eastern Hemisphere on July 13th. And we can see most of the continents from Africa to Europe to Asia suffer from very, very high, extreme, or even record-breaking heat waves. So with temperature about 40 degrees in many places. And one severe consequence of this global warming is the drought. So in recent years, historic levels of drought have been ravaging numerous regions worldwide, including the United States in particular, as shown in this diagram, over the past 2 decades. The lower left figures compare Lake Mead, which is the largest reservoir in the States, in 2000 with adequate water storage, and in 2021 at a record low. In this lower right corner is the US drought map in July 2021, showing that extreme levels of drought were really gripping the entire Southwest. So this ongoing mega drought in Western United States is demonstrated to be the worst or driest period since at least 1,200 years ago. What's making the situation worse is the ever-increasing human population, which together with the drought are really bringing water security to a tipping point. If we think about the source of fresh water supply, taking California, for example, in a dry year, just like these days, over 60% of the fresh water supply comes from groundwater. So in urgent demand now is really a refined understanding about groundwater aquifers. Ideally, we would hope to know both the spatial structures as well as the temporal variations of groundwater systems. So speaking of California, what else is it famous for? Since I'm giving this talk in seismology lab, you know my answer is Earth first. So for many seismologists like me, or many of you in the audience, whenever California is mentioned, the key word appears in our mind is neither drought nor flood. It's earthquakes. As shown on this map, California is highly prone to seismic risks due to all the known and unknown faults. And for a place like this, we know that there must have been or will be tremendous seismic stations. I know Richard has a much better map than I do here. But so initially, most of these seismic stations are designed for earthquake early warning system or for the studies of tectonics and faulting. But it will be super if we can also use them to deal with droughts. is gonna be Bellman Galvan radio for both USGS and for the community. So in my talk, I'll explore whether and to what level we can use seismic data to help monitor aquifers. So here is an outline of my talk today. It contains mainly 4 parts. The first part is a brief introduction to aquifer monitoring. The second part is about the methodology on space-time seismic interferometry. In the third part, I'll use a pilot application in metropolitan Los Angeles to study the groundwater fluctuations. In the last part will be some of my thoughts and discussion looking forward. On the outset is an introduction to the current status and challenges of aquifer monitoring. So first, let's look at the typical structures of groundwater aquifers or water barrier formations. So this is a slice typically from the Earth's surface to a few 100 meters below the surface. The tree is not to scale. It shows nicely the layer structures of shallow sediments. So we have this type of layers, mainly made of clays with finer grains. There are also this type of layers, mainly made of sands and gravels with coarser grains. And we know that the groundwater are held in the pore space among the sands and gravels with coarser grains. And these layers are called aquifers. These aquifer layers are interbedded among the clay layers with finer grains. Those clay layers typically bear very little water. So how to know the amount of water hidden in these underground systems? The most traditional way is to drill a well and to measure the hydraulic head or groundwater level. People tend to think of this hydraulic head data as ground truth because they are very direct and in situ measurements. However, each well only gives a point scale measurement at exactly where we drill. We don't know what's in between 2 wells or what's shallower or deeper. But in realistic, we know for sure that the aquifer structures are highly non-uniform at multiple scales. Due to the expensive cost of drilling and maintaining those monitoring wells, the sampling, the spatial and temporal sampling of well data are still very sparse, far from sufficient to capture the groundwater aquifer structures. So it's still pretty much like in the blind man and the elephant's parable. If we use the point scale well data alone, our understanding about the aquifer structures can be strongly biased by very small scale heterogeneities. So in recent years, GPS and InSAR have also emerged as very attractive tools for aquifer monitoring. The basic idea can be shown on this famous example on the right side. So this photo is taken in San Joaquin Valley in Central California, where the groundwater depletion has been excessive due to the high demand for irrigation. Shown on this map, the signs on the pole indicates the altitude of ground surface in different years. For example, in 1925, ground surface was over there, and in 1977, it was over here. So this indicates about 9 meters of subsidence over half a century, which is pretty dramatic. So the basic mechanism for this drastic subsidence or uplift is that this poroelastic aquifer or sediments medium are acting as poroelastic sponge soaked in water, just like this. So if we could measure at the surface how much this sponge is dilated or squeezed, we would be able to infer the changes in pore pressure and thus groundwater level. So this approach has really helped significantly benefiting from the high precision and temporal resolution of GPS and the high spatial resolution of InSAR. Although the challenge is that we know this surface deformation measurement lack the important resolution or even sensitivity to depths to processes at depths. Also, in realistic, at the end of the day, what people are really interested in is the groundwater storage. But it's quite challenging actually to translate or transfer this displacement measurements into the groundwater storage without a good modeling of all these elastic loading and inelastic factors. So there are also some other space sensing or airborne sensing techniques. For example, the airborne electromagnetic surveys or the satellite groundwater. But these methods suffer from similar limitations. So what I'm gonna present today is a seismological observation. We hope to use that to bring new perspectives for aquifer monitoring. Specifically, the quantity we measure is delta V over V. Here, V means seismic velocity or the propagation speed of seismic waves. So we know that this seismic velocity is unique to the mechanical state of crustal rocks. For example, at higher effective pressure, seismic waves propagate faster and vice versa. Then this delta V over V together means the relative changes in seismic velocity. So it pertains to changes both in time and in space. The idea for us is to associate this delta V over V with the hydrologic properties of the rocks. In other words, we try to measure the variations in delta V over V and use that to track variations in groundwater volume. So this idea of using delta V over V to track water content changes has long been used in laboratory scale rock physics experiments. But only recently have seismologists been able to measure it continuously in realistic scales. So how to do that? The answer lies in the second part of my talk, the space-time seismic interferometry. First, let's look at the time dimension. That is how to measure delta V over V continuously in time. This incorporates seismic interferometry in two steps. The first step is seismic interferometry of ambient noise. So the basic idea is that the Earth's surface is vibrating all the time, everywhere, as I speak. It's just most of the time, those vibrations are too small that we human beings don't really notice. But those ambient vibrations or ambient noise are being continuously recorded by seismometers. As shown here by the green waveforms, those ambient vibrations most of the time are really noisy and somewhat random. However, in recent years, seismologists have shown mathematically that by calculating the wave interference between this seismic ambient noise, we can actually retrieve very useful information called Green's functions that describe the properties and structures of the underground medium between two seismic receivers. So this idea of retrieving Green's functions from ambient noise interferometry has been applied in many problems. The representative ones are ambient noise tomography and vertical source ground motion predictions. So today I'll use this method for monitoring applications. So we can repeat, if we repeat this ambient noise interferometry during different time periods, we would be able to retrieve the Green's functions, say at consecutive dates or different times. Then the second step is coda wave interferometry. So coda waves are these later arrivals on the Green's functions. Those are typically waves come from the multiple scatters in the subsurface. And by analyzing the time shifts between the coda waveforms, we can calculate delta V over V. Note that there, for the traditional coda wave interferometry, there is one very important assumption, that is the medium variations are homogeneous in space. So with this assumption, the dV over V, delta V over V we want to calculate is just the opposite of delta T, the time shift over. So this idea of combining ambient noise interferometry and coda wave interferometry will allow us to continuously measure delta V over V time changes. And this idea has been applied in many geological settings, including for aquifer monitoring in particular. For example, shown in this study or several other studies, they compared the delta V over V time series and the groundwater table. So here, the blue line is the groundwater table, and the black line is the opposite delta V over V. So it's plotted in reverse direction. So they observed this evident anti-correlation between delta V over V and the groundwater table, which shows the proof of concept of using delta V over V to monitor groundwater storage. However, as I just mentioned on that slide, one important assumption for this traditional seismic interferometry is that they assume the medium perturbations are homogeneous in space. In other words, they were only able to calculate the temporal changes of delta V over V, not the spatial perturbations. But needless to say that if we really want to know how the physical process is involved in the subsurface, the spatial variations would be key. So in our study, we go one step further to push this seismic interferometry into a new level by also imaging delta V over V in space. So this was made possible benefiting from some recent developments on theoretical distributions of Coda waves. So, or to be more precise, the Coda wave sensitivity kernels. As shown on this map are Coda wave sensitivity kernels at different lapse times. So these kernels, the idea is very similar to finite frequency kernels. So they describe the likelihood of Coda waves travel paths. So with these kernels, currently on latitude, longitude plane, we can connect the delta V over V with the delta T time shifts at different lapse time. So this equation may appear familiar to you as in many geophysical problems, which means that we can then derive delta V over V by solving an inverse problem, where the G matrix, the design matrix consisting of all the kernels that we can theoretically calculate. And the D vector consists of all the DT that we can directly measure from the Coda waveforms. And then the model parameters we invert for are delta V over V at different locations. So,
quick question.
Yes.
I was trying to let you finish your sentence. These are multiply scattered waves, right?
Right.
So it kind of looks like a diffusion problem.
Yes. So
those kernels look like solutions to diffusion equation.
Well, it's to be more precise, it's based on relative transfer equation. So we didn't make any assumption of diffusion regime. That's also one improvement of our kernel compared to previous kernels.
Can I have one more question?
Yes.
So, but do you think the kernel could be different by region, like LA region kernel, this one, maybe San Francisco, different kernel?
Yes, they would be kind of different because the velocity model and
Right.
the scattering properties would be different. So here, for now, for this LA case, we just use the homogeneous model. And I did try a range of parameters for the scattering mean free path. That doesn't change my result.
Okay, thank you.
Yes, thank you for the question. For this case, we just use a very simple inversion approach with the classic Tarantola recipe. So if we repeat this type of Coda wave imaging at different times, we can get the time-dependent images of delta V over V, which basically are the space-time measurements of delta V. Now let's have a brief idea on this space-time delta V over V measurements. So the lower map shows my study area in metropolitan LA. The time series of delta V over V at this location is shown on the top plot from 2000 to 2020. And I'm gonna play a small movie to show you the delta V over V measurements everywhere in this map. And you are gonna see bluish color corresponding to more groundwater and reddish color corresponding to less groundwater. So the detail feature in this movie I will discuss later in my talk. Just here you can see a general change from bluish color. You see at early stage it's pretty bluish, and gradually changing into reddish color, corresponding to an overall decline of groundwater in the study area. So on the right side is a comparison with INSAR and GPS in terms of resolution. We know that GPS excels in its high temporal resolution and INSAR in high spatial resolution. And our delta V over V falls around here. So to some degree, it kind of incorporates both the advantages of GPS and INSAR. I also want to emphasize that very different from surface deformation or deformation measurements in general, delta V over V essentially reflect changes in mechanical properties of the rocks. So to be more precise, it's determined by elastic moduli and bulk density. So our delta V over V is often related to deformation, but not the same as deformation.
Can I ask a question?
Yes.
So the map that you just showed, the animation you just showed, you're just showing us one velocity over time. So say something about depth. So what's the depth sensitivity? Is it just you have one measurement as a function of latitude and longitude? And what kind of depth sensitivity do you have and why?
Yes, that's a very good question. I guess I'll answer that in my later slides.
Perfect.
Okay, so as you said, yes, this is the measurement at one depth or to a range of depths, the average over a range of depths. Yes.
But this is 0.2 to 2 hertz, right?
Yes, yes, exactly. Oh, I didn't. But so what's very important is that these are subsurface properties rather than say surface measurements. Okay, so in this third part, I'll use this pilot application in metropolitan Los Angeles. First, I'll briefly go through the hydrogeological background here, and then we will look at the temporal changes and spatial distributions of delta V over V, respectively. For this application, I hope to use it to show you one, the validity of our delta V over V imaging approach, and two, how delta V over V could help us to understand underground hydrologic processes. So here is our study area in metropolitan LA, comprising a number of groundwater basins. Primarily are this Santa Ana Basin and LA Central Basin. So these basins are mainly bounded by mountains and faults, which can serve as natural barriers for groundwater flow. They are also partly partitioned by municipal borders. And note that each of these basins is managed by a local water department. So the groundwater storage in this area exhibits strong seasonal fluctuations due to recharge by precipitation in winters and withdrawal of groundwater due to highway pumpings in dry summers. And one significant feature in this area in the two major basins, Santa Ana and LA Basin, LA Central Basin, is that the northeast side is characterized as a unconfined zone or forebay area, mainly consisting of aquifers with sands and gravels. In contrast, the confined zone consists of aquifers interbedded among the clay layers that's recharge groundwater flow. So due to the very different compressibilities of the sediments in these two areas, the confined zone could deform drastically corresponding to the seasonal groundwater fluctuations. So this is basically the spongy part. In contrast, the unconfined zone doesn't really deform much. To calculate delta V over V, we use about 50 broadband seismic stations in metropolitan LA operated by USGS and Caltech. So here on the right plot, I show the blue line shows the temperature changes of delta V over V from 2000 to 2020. So this measurement is averaged over the entire study area. And you could note that the vertical direction of delta V over V is plotted in reverse way and for a more intuitive comparison with groundwater. So now upwards means more groundwater. And the gray line shows the long-term trends of delta V over V. The light blue bars on the bottom show the annual cumulative precipitation. So this gray line indicates that shows an overall decreasing trend over the past 2 decades, suggesting an overall decline of groundwater in the study area due to the long-term dearth of precipitation. So this decreasing trend was interrupted by several briefly increasing episodes corresponding to years, you can see with some storms. And the blue line shows that superimposed on these long-term trends are also some seasonal fluctuations associated with the seasonal hydrologic cycles. I also want to mention this year, which was quite interesting because I learned that for this year, people observe some both extensional and uplift signals, very significant signals from GPS station in the San Gabriel Valley. And people were wondering if there was a big earthquake or some deformation, aseismic deformation or deformation related to faulting. But it turns out to be just a year of very abundant rainfall. Okay, so this is the measurements average over the entire study area to give us a general impression. For a more localized analysis, now I zoom into Santana Basin. So the blue line is delta V over V again. It's just this time, it's only averaged within the Santana Basin. And the yellow line with circles are the hydraulic head measured by a local monitoring well. So you can see over the past 2 decades, these two match very well with each other, both for the long-term changes and for the seasonal variations, which indicates that we could probably leverage the large number of seismometers in California as an alternative way to track groundwater levels, which could be very promising because it will considerably improve the temporal and spatial density of, say, water level measurements, while avoiding the very expensive cost for drilling and maintaining groundwater monitoring wells. Okay,
Can I ask one question? Sorry.
Yes.
This is fantastic, but I was wondering now the convert to the dB over V percentage to the hydro. I don't know. I can read it in the in the meters. So is there any like a conversion factor is same as everywhere, or this is only the area you can convert to the dB over V percentage some meter?
Yes, that's an important point. So in our study, basically, we only show this correlation between or any correlation between the two. And we didn't try to quantitatively interpret delta V over V. If we have a very good modeling from high data to delta V over V, we will be direct.
Okay.
Yes,
So
there have been, sorry.
Go ahead.
Yes, it's just that there have been some first order modeling taking into account the loading of the water and the poroelastic strain. So to translate from this head data into delta V over V, but that didn't really take into account if it's confined aquifer or unconfined or.
Well, depends on the program. Okay, thank you.
Right. Okay, so so far we've been looking at these temperature changes. Now I move on to spatial patterns. So first is this imaging of seasonal changes. So we divide the study area into 2 kilometer by 2 kilometer pixels and calculate delta V over V at each pixel. On this map, the color at each pixel indicates the amplitude of seasonal variations of delta V over V on that pixel. And you can see from this map, the dominant seasonal changes in reddish color concentrates in Santa Ana Basin, with the borders pretty consistent with the basin borders. We can also observe this very sharp gradient along the four-way boundary, and the dominant changes concentrate on the confined side, which makes sense. We can then further substantiate this delta V over V image by comparing it to deformation inferred from INSAR. So on the right side, to be more precise, is the measurement of vertical displacement at the surface. Whereas our delta V over V is a measure of elastic moduli and bulk density at depths. But despite measuring different physical properties, these two maps show largely consistent patterns, both with dominant changes in the confined side of Santa Ana Basin. The main difference between these two images is probably this reddish area in LA Central Basin, appearing on the deformation map, but missing delta V over V. So the answer or the reason to this difference is that, as Richard just suggested, for this delta V over V map, it's measured within one frequency band. So we know that one unique ability of our seismological observation is that seismic waves of different frequency bands probe the underground structures at different depths. So if we measure that at different depths, now from left to right or up to bottom, are using decreasing frequency bands corresponding to deeper and deeper depths below the surface. So you can see from shallower to deeper depths, the reddish portion seem to migrate southeastwards from LA Central Basin to eventually Santa Ana Basin, indicating that the dominant seasonal changes migrate southeastwards. Also, consistently across different depths, all these dominant changes are concentrated on the confined side. If I display the INSAR map again, we know that the surface deformation can be seen as an integration of strain at different depths. So to some degree, these INSAR images can be seen as a sum of the delta V over V changes at different depths. And it is true, as we expected, if I sum up these three images, they began to assemble these features on the INSAR map. And so compared to INSAR, you can see delta V over V further helps to characterize the aquifer behaviors and their hydrology at different depths. So this depth information can be quite helpful for decision makers in water agencies to optimize their pumping and drilling strategies to promote the sustainability of groundwater management. Okay, so in the last part of this LA case study, I want to show you the imaging of the long-term changes. So showing here are delta V over V accumulated from 2000 to 2020. The bluish color corresponding to an cumulative increase of groundwater, and the reddish color a cumulative decline. So you can see in San Gabriel and LA Central Basins, there seem to be much less water now than in 21 years ago. In Santa Ana Basin, however, the water seemed to recover even with a slight increase compared to decades ago. So this was very interesting for us seismologists because we know that this boundary between the two basins is not a fault. It's just a county line. So LA, Los Angeles County on this side, Orange County on this side. So why we observe such a big difference even of the signs of cumulative changes in these two adjacent basins?
Excuse me, is this at a given frequency?
Yeah, are you asking, is it measured with certain frequency?
Well, you showed that the maps look different at different frequencies. So I'm wondering whether this is at a specific frequency.
Yes, exactly. In the supplementary material of our paper, we showed the images at a different frequency. The different signs are pretty similar for these two basins. It's just at shallower depths, the groundwater decrease in San Gabriel Basin is less. Also, the patterns for this LA West Coast Basin is a little bit different because the situations there are more related to the seawater intrusion and those type of issues.
Excuse me, is the LA Central Basin and the Santa Ana Basin have the same hydrogeology?
Very similar.
Very similar?
Geology, because yes, it's basically geologically it's the same basin. It's just divided geopolitically. And over all these years, well, you will see. So we try to analyze the difference, the reason for this difference by looking at two seasonal components. So here is the delta V over V time series over the 2 decades average within Santa Ana Basin. And we know that for a given year, the net changes of groundwater is mainly the sum of two factors. That is the rainfall induced increase of groundwater in winter minus the pumping induced groundwater decrease in summer. If I plot the relationship between these two seasonal factors over the 2 decades, here horizontal axis indicates rainfall-induced delta V over V, and pumping-induced changes on the vertical direction. Also, one more small detail is that note that this diagram is purely derived based on delta V over V data. We didn't have the pumping data or the groundwater changes over the entire study area. And also, yes.
Sorry, finish your sentence.
Yes, and just another small detail is that to avoid extreme estimation of weather factors and also to follow the practice of Santa Ana Basin, this rainfall-induced component is average every 3 years. Please.
So I'm missing something, but so how do you know it's pumping induced change in dB over V, and how do you know it's rainfall induced?
Yes, because rainfall in LA area is mainly occur in winters. So we take the difference between the peak value and the valley value here as the
I see. And then
rainfall induced delta V over V, and then the pumping mostly occur in dry summer. So that's as the pumping.
so you're assuming that the decrease in the summer is all due to pumping and the increase in the winter is all due to rainfall.
Yes, exactly. That's a
Okay.
very simplified
Yep.
assumption.
Got it.
And you could see if with this assumption, we can see in Santa Ana Basin, these two factors correlate linearly with each other, suggesting that in Santa Ana Basin, they were able to manage the pumping in a very nice way. So they adjust the pumpage based on the rainfall data. So in humid periods, they pump more, and in dry periods, they try to increase the price of the pumpage to decrease the amount of pumping, which in the long term shows a long-term balance of groundwater storage in this case. However, this has not been the case for the other two basins as shown on the left side. We observe very little evidence of linear relationship between these two seasonal components. What's more, you see for San Gabriel and LA Central Basins, there are more dots on the upper triangle corresponding to years when pumping-induced changes exceed the rainfall-induced changes, which altogether progressively lead to the long-term excessive groundwater depletion. So this type of analysis shows that the different pumping strategies is likely the main reason for the all the signs we observed in these basins. It shows the significant roles of anthropogenic activities on shaping the shallow subsurface, compounding the global warming. So this type of effect can now be verified and quantified with our seismic observations. It also shows that by putting into practice very nicely managed water strategies, we can indeed make a big difference in the long term as shown in this Santa Ana Basin. In addition, it shows that WRV can serve as a way to assess or estimate groundwater budgets. So this observation is independent from traditional estimation based on stream flow, precipitation, or well data, which could subject to big uncertainties if we don't have a good model of aquifer structures. Yes.
So do you have any evidence of the pumping strategy of the different countries?
Actually, from the report of Santa Ana Basin, they said that in their we have this report every 5 years from the water department. They say that they did apply this strategy, so they give a quota for groundwater pumping every year based on the rainfall, the modeling of groundwater storage, the estimates for the previous years. And once the pumping or the pumpage exceeds this quota, they increase
I see.
the
Okay.
price.
Yeah, that's great to know. Because like I first thought like the reddish color on the map is of course related to the like pumping induced dB over V, because like your pumping related induced dB over V is estimated from the winter summer part of the decrease itself. So it's almost saying the same thing, because like average over the more decrease, larger decrease means upper triangle in this diagram.
Sorry, I didn't catch this part.
Yeah,
Yes.
like you have more orange
Yes.
part,
Yes.
and then that's why the map is reddish and you have a triangle, but they're both from the same color. So that itself doesn't really prove that is related to pumping, because there's other reasons like the water, like groundwater, can flow to other places. Like
Yes.
groundwater
Yes.
that doesn't really decrease only from pumping. Like there's other reasons.
Right. So if those things, so the accumulated changes is the sum of these net annual changes over all these years. But if we separate these two seasonal factors, you can see. If we separate these two factors, you can see this pattern. These two patterns are very different. And about the runoff and those flow you mentioned, so for the surface stream flow, we didn't take into account because, for example, the water that flows or drain into the Pacific Ocean, we didn't. Those are not measured by our WRV because those are very surface properties. What we are measuring what's really happening at depth. There are some groundwater flow between these two basins because there is no hydraulic area, but over the time it emerges this gradient between the water.
The depth you show is, I think, the peak sensitivity depth for surface waves. Right?
Yes.
So you have some sensitivity of surface too.
Yes. So well, I didn't have that here. But for the depth sensitivity, yes, we have two peaks. One big peak very close to the surface, and one big peak at depth. And we think this type of changes are more related to the deeper peaks because the images at different the amplitude at the different depths for different frequency bands are consistent. Because if you look at the shallower peaks for different frequency bands, the amplitudes are so different. If what you're measuring are really the shallow thing who's running the shallow peak, then the amplitude you observe on this different frequency band will be very different. There are indeed some features we think are more related to the shallower peaks, but
Excuse me, I have a related question, I think. So basically what you're showing are maps of sort of like a group velocity of surface waves, basically, right, at different frequencies. That's what you get. Have you tried inverting this with depth? Because you have basically an average velocity, regionally, regional variations in the velocity, in a group velocity, essentially. And then you can invert that with depth to get a more, have you tried that, or is that?
Yes, that's an important aspect. So to be more precise, what we're measuring now, because we're using Coda waves on the Green's functions, rather than say direct surface waves
Sure.
or body waves. So for Coda waves, it's a mixture, although it's mainly consists of scattered surface waves, but it's a mixture of surface waves and body waves.
But it's mostly surface waves, though.
Yes, for this case, it's mostly surface waves. For this case, we didn't try to invert for the full depth profile, as I will mention later, because for this dV over V measurement, we use, say, short window Fourier transform to calculate the dt. So that only gives us, the measurement over a pretty broad frequency band. But what we are doing right now with data in Texas, Delaware Basin in West Texas, for that data set, we are using a new approach based on Wigler transform, which gives us dt measurements with very fine frequency resolution. So with that, we could have delta V over V measured at each frequency. And then we can invert really for a full depth profile.
Thank you.
Does that answer your question?
Yes, thank you.
Thank you. Okay, so to conclude this LA case study, we measured the spatial temporal variations of delta V over V in metropolitan LA from 2000 to 2020. And the temporal changes of delta V over V was verified by the hydraulic head measurement, and the spatial patterns of seasonal signals are verified by INSAR image. Also, compared to previously existing methods, delta V over V further helps to characterize the aquifer behaviors and their hydrology at different depths. Also, in the spirit of from science to solution, from knowledge to action, delta V over V can also serve as a new type of observation to promote the data-informed water management. So it's independent from the other traditional observations and can complement those estimations or modeling. One particular point I also want to mention is that in 2014, California passed this historic legislation called Sustainable Groundwater Management Act, or SIGMA. So SIGMA was enacted to make sure that the groundwater is managed for long-term reliability. So it sets forth a statewide framework where the California Department of Water Resources provides grants, data sets, and scientific analysis to the local water agencies in order to implement and develop groundwater sustainable plans and projects. I learned that as part of this framework, there are already efforts going on to incorporate the models derived by seismic refractions into the statewide groundwater flow model. So now that we have this abundant spatial temporal measurements of delta V over V, I'm sure there are a lot more things we can do and to really be a very helpful part of the water solution. So with this LA case study, I hope I've convinced you that delta V over V can be a very promising data set. It's cost-effective, non-destructive, and very useful for long-term monitoring of groundwater aquifers. But this LLAC study is essentially just a pilot application illustrating the level of info we could provide. And this space-time seismic interferometry is still very, very new technique. Looking forward, there are still many aspects to improve and to explore in order to fully exploit this delta V over V data sets. So now I'll move to the last part, looking forward. First, we know that the power of delta V over V is certainly not limited to aquifer monitoring, because as a matter of elastic moduli and bulk density, delta V over V can pick up changes related to fluid content, stress field, and rock damages. So those type of changes are associated with a broad spectrum of time varying processes. For example, the aseismic deformation and volcanic activities. One example is this famous study by Bangui et al., where they analyzed the delta V over V at Piton Delphinez volcano at La Réunion Island. So they measured the temporal changes of delta V over V and observed this red parts, the precursory signals prior to the volcanic eruptions. Those signals are due to the pre-eruptive pressurization in the magma chamber. So those type of delta V over V precursors can be used to forecast volcanic eruptions. There are also many other topics that delta V over V can be used to monitor. For example, the fluid injection and extraction in oil and gas fields or geothermal fields. For example, this one here. Also, some other processes related to the carbon sequestration and freeing and thawing processes. So most of the topics here have been actually analyzed in previous papers, but those studies only employs the traditional seismic interferometry and only measures the temporal changes. Now, with this new imaging approach, I believe there will be tons of new information for us to explore. From a technical perspective, one key advantage of delta V over V is really this depth resolution, because for example, essentially all other methods for aquifer monitoring do not have this very good depth resolution, especially for deeper aquifers. So in this LLAC study, as Barbara just asked about, we only provided the images at 3 different depths, limited by the short window Fourier transform we use. But now we have developed and are applying this new technique based on Wigler's cross-vector analysis, which gives us dB over V measurements at a very fine frequency resolution. So with that, we will be able to provide a full depth image of delta V over V. Also, regarding the aerial resolution, for the LLAC study, I was lucky to have a very good station coverage, very dense one and very even station distribution. So I just use a very simple inversion approach, but with regular grid meshing. But that doesn't work well for a more universal case of irregular station coverage. For example, in Central California, the stations are spaced at multiple scales, very irregular. Another question I got asked all the time when I talk to hydrology people is that what's my aerial resolution? So to deal with this two problem, we are now developing a new imaging, coda wave imaging approach based on Voronoi diagrams. So we could provide grid meshing, irregular grid meshing, adaptive to the station distribution to provide optimal aerial resolution at different areas. And also based on this approach, we would be able to provide a quantitative resolution analysis. For example, as shown here, within this dark gray contour, we have a resolution where we have confidence of 10-kilometer resolution. And within this lighter color contour, we have 20-kilometer resolution and 40-kilometer resolution. Okay, then from a practical perspective, also as Taka asked, to really directly use delta VORB to for water management, or say other applications to dictate the decision making, we really need to quantitatively interpret delta VORB. So what I showed you today is only this correlation. It's a very good correlation, but looking forward, we must have a very good modeling from head data or other, say, practically interesting physical properties to delta VORB, to really understand and use delta VORB. Last but not least, another important direction, also one direction that I'm personally very interested in, is to integrate delta VORB with other types of data. For example, here I compare delta VORB and INSAR in multiple aspects. For example, the horizontal resolution of INSAR is almost parallel. And the depth resolution of delta VORB is really unique. So you can see these two really excel in different aspects, and they could really complement each other. In the meantime, we know that these two are measurements of very different physical properties that are sensitive to quite different processes. For example, we know that the saturation changes in Beddoes zone may not lead to substantial deformation, so it's often invisible to INSAR. But those saturation changes can cause substantial changes of delta VORB. So if we could combine the different perspectives from the different physical properties measurements, DVORB and INSAR, and perhaps other types of measurements, we would be able to constrain the true subsurface processes much better. Last page, I want to acknowledge, first of all, my advisors. So most of the ALEC study I showed you today are guided by my PhD advisors, Michel Cambil from staff in France and Professor Robert Fust at MIT. Also, most of the current work I'm doing in Central California and West Texas are guided by Professor Greg Braza, Professor Bill Ellsworth, and Professor Rosemary Knight at Stanford University. Also, a lot of other collaborators who made very important contributions to the work I mentioned today. And I would also like to thank a lot of people for insightful discussions that I benefit a lot. Also, Roland, who is here today, he is the reviewer of our paper and provided many insightful suggestions. And the funding for this research coming from the European Research Council and the Thompson Fellowship at Stanford University. And thank Roland again for the invitation, and thank you all for your attention. With that, I'd be happy to answer your questions.
So we're a little over time, so maybe we'll just have 2 or 3 questions, and then we can continue on the balcony outside. Oh, Chief.
All right. Your last application for unconfined aquifers. The unconfined aquifers, as you said, shows little delta V over V, right?
Yes.
Okay, so how do you apply this technique to the unconfined aquifer?
Yes, if you compare, so as you can see on this page, so it's true that in unconfined zone, the changes are much smaller, but if you compare that to INSAR, this is cyan color, different from the blue, dark blue color. So we do, compared to INSAR, we do observe better signal. And also,
Okay, so it's not direct.
you see signals, it's much weaker, that's true, compared
Yes.
to the reddish color, but still we do see signals on the sign.
Okay. Okay, thank you.
Okay,
Is the sign what you expect in the unconfined aquifer?
Yes, that's a very good question.
Because
So,
density goes up and velocity may not.
yes, the saturation,
Yeah.
the saturation tables, we would expect a different sign as in confined zone. That's a very good question. But essentially, all current studies of delta V over V, either in confined zone or unconfined zone, only observe the opposite signs of delta V over V on geodetic pyramids. That's something worth investigating too.
okay. Anybody else? Last chance. Okay, then, oh, okay, sure. Last question.
There's still
Somebody
time.
online. Barbara, yes, go ahead, Barbara.
Well, anyway, thank you for a great seminar, Shujuan. And I have a question about your inverse process. Is it an iterative process? Do you actually iterate your inversion and change the kernel as the model evolves, or is it just a one step?
Yeah, so I did use 2 or 3 iterations, so it's not like a lot of iterations in this case.
But you change the kernel at each iteration?
The kernel, I didn't change the kernel, it's just the starting model is at the very beginning, the starting model is all zeros. And then I adopt the prior model subsequent.
Thank you.
All right, let me remind everybody, we'll have drinks on the balcony, so please come and ask your questions. And let's thank our speaker again.